So I'm going to start by just summarizing what we said last. We were talking about potential scattering, so scattering of neutrons off a static potential. So we have a very, very simple description of the material that we're scattering from. It has no dynamics whatsoever. And it is simply, this problem is described by a Hamiltonian which has two terms. One that describes the free neutron in its propagation, and one term which is the interaction potential between the neutron and the material. And where we ended up, I think, in the last lecture, was we showed how to obtain a scattering state which was at the same energy as the incoming neutron state. So we start off with some chosen energy for the neutron, and then in response to this potential, that stationary state develops into a new stationary state which is influenced by this potential. And we actually developed the position. I'm just going to sort of jump into it since we saw the calculation last time. There was a plane wave term that describes the incident neutron beam as such. And then there was the term which I'm constantly warning you will end up being related to our scattering cross-section. This is describing the effect of the potential and has a very nice and simple form, in fact. Here's the plane wave, and here is a spherical outgoing wave. So this is a wave that is emanating from the center of scattering. And it has in front of it a prefactor which we call the scattering amplitude. This prefactor can have angular dependence to it. So this one will contain all the interesting and detailed information about the material itself. And we have an expression for this scattering amplitude, which I'm going to write down here. F of theta equals to minus 4 pi squared m over h bar squared. And then a matrix element involving the so-called T operator. Okay, what is that operator? Just to remind you, and I'm going to have to ask you to switch to the middle section. What that operator looked like is as follows. T was equals to V divided by 1 minus GV. G was the propagator for the free neutron. V was the interaction potential that we saw in our initial problem. And we actually looked a little bit at this expression and were able to develop something that we call the Born series, where the T operator is written as V times a summation all the way from 0 to infinite of GV quantity to the nth power. So a lot of terms in that series, but only the n equals to 0 term is... if we include only the 0 term, then we have what we call the first Born approximation. And in that case, T is simply approximated as being equals to this scattering potential. And that's a good approximation if the interaction is not actually too strong. Okay, so there you have where we essentially arrived at the last lecture. And I'm going to briefly pause here to mention to you that I have developed some homework, so you pay good attention to the lectures that goes on. 5 nice little problems for you to enjoy, in which you will go over some of this material, and you will also be putting in various numbers to try to get a bit of a sense of how to apply this type of stuff in more realistic situations. Now, I should mention that the book I'm using is this book. Most of what I've been saying can actually be found in that. It's Varley F. Sears Neutron Optics, and you will see the reference for that one on the course webpage. Also posted on the course webpage will soon be my handwritten notes. Now those are actually mostly intended for the for yours truly, but I've tried to write them a little nicer for the second lecture, so you can try to follow along if you need to do that. So I think between those pieces of information, you should be able to solve these 5 homework problems and hand them into your to your professor, or you can simply solve them and look at the solutions that will be posted online next Thursday. All right, so that was the Born approximation, t approximately equals to v. Good. So now what I'd like to do is to actually use this real space stationary wave function to try to understand what it is describing in terms of the scattering process itself. And it actually has all the information that we need buried within it. Of course, we started off looking at a time-independent Schrödinger equation. So these are stationary states in which there's no time showing up. So you could ask, where am I going to see my current density, which we need in order to be thinking about a scattering situation. And of course, what we have to do is develop from the time-independent wave function a time-dependent wave function, which would now have both a position variable and a time variable. And then we would have the time evolution term, or this phase factor will show up. Remember that it's a state of a definite energy, so we just have this very simple phase factor appearing, and then comes the spatial part of it following on to that. So that's what the time-dependent wave function is going to look like. Then I can ask, what is this actually describing in real space? And of course, we would like it to describe a certain density of neutrons. The density of neutrons would be related to, which is now a position-dependent density. That would now be related just to the mod squared of this whole wave function. But this guy, being just the phase factor, doesn't end up showing up there. It's a stationary state. So I'm just going to get some sort of mod squared wave function, which will tell me the density of neutrons through space. I can also get a current density, which will depend on position, and this one would be equals to real part of. And this is all basic quantum mechanics that you probably have seen before, but it's a nice little application of it. We would take the complex conjugate of the wave function. We would take the velocity operator, that means 1 over mass, and then h bar over I del operator, and have that operate on phi k of r itself. So this is how I would get the current density out of this expression. And from this wave function, I can get the current density anywhere that I would like to see it. Now, there's a little something I have to say about normalization. So far we've kept this type of normalization of our wave function because we wanted actually, it had to do with wanting the plane wave states to be the normal ones that we are familiar with. But now I would like to actually use this to describe a sort of real physical situation of scattering. Oh, I have to be careful there with the camera. And so therefore I'm going to slightly change the normalization. I would like my wave function, instead of looking like that, and would you pan the camera over here? I would like to modify it in the following sense, so that rather than this prefactor, I would like to just have a density of neutron prefactor showing up. It's not the density of my material, it's the density of neutrons. This will just ensure that that this expression actually comes out correctly. At that point, I can now go and derive from this the differential scattering cross-section. And for that, I'm going to take one more step in this direction. And let me remind you what the differential scattering cross-section looks like. This is the symbolic form that we had. And this was to tell us the amount of neutrons detected within our solid angle of the detector system, d omega, divided by incident flux per time per area, and multiplied by d omega. That was what our differential scattering cross-section should look like. And so now what I can do is I can just develop the numerator and the denominator and then introduce these types of expressions. So up here I need the number of neutrons which arrive in my detector. Let's give the detector an area dA. That means that the number of neutrons would be the incident current density dotted with dA. This would be number of neutrons per second. And then I would want to divide by the incident flux, which we could call, let's call this one J prime, because this one has to be, let's call it J prime because it has to be evaluated close to the detector. I'm just going to call it J prime. It's the same function, but I'm just putting an R which corresponds to where that detector is. Okay, so I call it J prime, and J will be my incident flux, and then I should also divide by d omega. Now d omega was the solid angle of the detector, which you remember was equal to dA divided by r squared, r being the distance from the sample to the detector. Okay, so now I can continue to use to develop expressions for these current densities, and let me look at those for the incident beam and for the scattered beam. So for the incident beam, the current density J of r, according to this expression, is going to be equal to the density of neutrons, and then so the density will come out from these two convex conjugated pairs, and then I'm going to also get my velocity operator del operating on this function, and remember that that's a plane wave type function, and so I'm simply going to get an h bar k divided by mass of those neutrons. So this is the normal expression you're familiar with for particles which are in motion. There's a density of particles times a velocity. It's not a current density because I don't have a charge there. So it's a neutral current, but there's a certain number of particles per time unit, and this is described by that current density. So that's the incident current density, and the scattered current density, which I'm calling J prime, for that I have to look at, and if you could just zoom over here, I have to look at this part of the expression, and I have to look at what current density does that describe. And it's going to be, again, the density shows up again, but then I'm going to see an f of theta mod squared showing up, and I'm going to see a 1 over r squared showing up. So that's going to be the current density at the location of the detector according to that real space wave function. Okay, so then I'm going to put those things in over here, and I'm going to see for J prime I get rho, absolute value of f theta squared, and then I have my dA from here divided by an r squared, which was part of this expression, and then I get to divide by incident current density, which was, one thing I forgot here was h bar k divided by m. That has to show up again. Came from the velocity operator here. Actually, if we want this to be a vector, then this guy would be my k prime, my scattered wave vector. That actually will come out correctly once I take the gradient of this type of term, and now you have to pan the camera. This type of term here, if I take the gradient of that, it will produce a k vector which is pointing towards the detector. So that actually all works out very nicely. So I'm allowed to actually have these graduate to be vectors if we would like. Okay, so pop this in. You'll see that on top I'm going to get an h bar k divided by m. And the bottom I still have my rho, and I have my h bar k divided by m. And I have my d omega, which needs to show up according to the denominator over here. All right, so now what happens is that this cancels, that cancels with that. The densities cancel, and I end up with a very, very nice expression, which is just mod squared of the scattering amplitude. So everything has been set up for this result to come out correctly, and that is actually the result that we're now going to be working forward with and give you various types of examples of that. So I think I'm going to come all the way over there, and I can now erase this. And I want to spend a little time developing the expression that we now can write down for the differential scattering cross section. So it was actually very, very simple, as we said. It was just mod squared of that. So let let us now introduce the expression that we had for this function. And let's see, I'm going to come back a tad. So here's my expression. So this is going to be equals to absolute value of minus 4 pi squared m h bar squared k my t operator. In the Born approximation, that becomes a v, but I'm going to leave it as a t for now to emphasize the generality of it. And so this guy is actually a k prime, and this is a k, plane wave state, and I have to take mod squared of that. Okay, so now I'm going to develop this a little bit. It's pretty trivial, but this is I like this point because it'll show you where the scattering vector comes out of the story. So just to see how this happens, there's a 4 pi squared m divided by h bar squared, and these I should now convert to my normal plane wave states and actually have a position space representation of this matrix element. So what that's going to do is it will produce a 1 divided by 2 pi to the third power from the normalization of those functions, and then there will be an integral in position space, so d3r, and there will be a e to the minus I k prime dot r. R is the variable I'm integrating over, and then comes my potentially generally r-dependent t operator. So this is the position space representation of that operator, and then over here comes my e to the I k dot r. That's the matrix element, and all of this has to be mod squared. Okay, good. So then let's look at this story here. What this will do is this produces a m divided by 2 pi h bar squared, and this factor will actually show up a couple of times as we go forward. So I'm very pleased to see that. These two I can now join together, and I'm going to get an integral d3r, and then I'll have tr, and then e to the I k k minus k prime dot r, and all of that has to be mod squared. And so at this point you've noticed directly, if you will, that this matrix element actually is a Fourier transform of the position space representation of the t operator, and what is the Fourier variable, if you will, is what we would call wave vector transfer. So I'm going to write that down here. It's a very important variable for us. So q is my wave vector transfer. It is the incident wave vector minus the scattered wave vector. So we could say it's related to the amount of momentum which is transferred to the sample in the scattering process. So with that definition, this becomes simply a q dot r. All of this is mod squared. Okay, so this is an expression we really like to have seen come forward, and you see that the only approximation we've had to make, it's a pretty serious one at that, is that we've had to say that it's a static potential, right? So we have no dynamics in the material at all, and we're going to introduce that at some stage. But for now, it's simply just that type of situation. But within that approximation, it's pretty general, actually. Okay, very good. All right, so now I want to talk a little bit about what this T matrix might actually go and look like if we're talking about the scattering from a single atom. Okay, so let's move along the board a little bit. So as you know, the interaction that is relevant here is going to be the strong nuclear force. And so the characteristic length scale that we're dealing with is the size of a nucleus. So scattering from a nucleus, basically. So the length scale that we're talking about here is going to be something on the scale of femtometer. That is sort of a characteristic size of the nucleus that we'll be dealing with. So in other words, 10 to the minus 15 meters, something of that scale. in our experiments, the wavelength of the neutron will be, so this is the size of the nucleus, the wavelength of the neutrons that we are going to be working with are going to be something from, let's say 10 to the minus 11 meter up to, we could go quite high actually, 10 to the minus 8 meters or even higher than that. But you can see that we'll never, or we will not, in most of the experiments we could consider, actually come down to length scales that rival that very, very small size of the nucleus. And so, as an approximation, it's appropriate for us to think about the position space representation of the T operator to actually simply behave as a delta function. Delta function in position space, something like that. And of course I want it to be dimensionally correct, and you'll remember that the T operator has dimension of an energy, right? It was V divided by 1 minus GV, GV being dimensionless, so it has dimension of an energy. And so to describe the scattering from a nucleus, what we typically will want to write down is something like 2 pi h bar squared divided by m times the delta function of r. But this won't be quite right because this one has dimension of inverse volume, and what I need is inverse area actually. So I need to multiply by a length, and that is what we call the scattering length. So all of this is, if you will, this is saying the nucleus is very small. This is what we need for dimensionally appropriate, to be dimensionally appropriate, and B is our scattering length, which is going to characterize the individual nucleus. And there's a little bit of a story that should be said about bound nuclei as compared to the true two-body scattering event, where the nucleus is not bound and we just have the two-body interaction between the neutron and the nucleus. And I'm going to sort of skip over that a little bit because I'm talking about a completely static potential anyway. So I'm going to think about the somewhat artificial situation of the nucleus just bound in space. And so in that context, this would be called the bound scattering length. Okay, good. So let me. So that's the way that we're going to approximate the nucleus. And let's see. Good. So then I'm going to take one more step here, which is, so far I was talking about the T operator, but I'm going to often be talking about situations in which I can treat the scattering as being within the first Born approximation, though there's sort of a subtle point here in that the scattering from the nucleus itself ought to be dealt with the full complexity of scattering theory, whereas the interference effects, etc., we can deal with in the Born approximation. But we will make a certain step here in which we will say, let me replace the instead of dealing with this T operator, I'm going to instead deal with a soda potential, which is the so-called Fermi soda potential, which has exactly the same form. Okay, and this potential works, if you will, if I treat it within the first Born approximation. So it's a little bit of a trick, but it works very, 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 very well. So we're going to treat the nucleus as if it simply has this type of potential, but it's understood that we should be using that potential for scattering calculations when we're working within the first Born approximation. So this is called the Fermi soda potential. And I just want to say a few words about a rather interesting, rather sort of, what should we say, non-intuitive behavior of this type of potential. And to do that, I think I'm going to want to come back here, actually. Okay. So I want to think about now a situation in which the neutron wavelength is going to be a lot greater than the inter-atom spacing. So that would certainly assure the limit that I would like to be in. But to be more specific, the limit I would like to be in is the one in which I have no inter-particle interference terms. So this would certainly be assured if I have a sufficiently long wavelength, but it can also be assured by the particular geometry that I'm dealing with. Suffice it to say that I want to treat my forest of delta functions, because that's what I get when I have a solid with a lot of these nuclei sitting in it. I want to treat this forest as basically sort of a smeared density. So I'm going to neglect the fact that they actually are in certain locations and just think of the whole potential as being completely smeared out in space. So this brings me into the limit of kind of like an electromagnetic description of the interaction between the neutron and the material. And what then happens is that the potential, which I'm going to be dealing with, is now going to be sort of the average of the potential over a sufficiently long length scale, but not too long, because then I'll lose all of the detail of the interfaces between the materials that I'm dealing with, etc. So I'm going to do the normal trick that we do in electromagnetism, and that basically ends up replacing in my soda potential the Dirac delta function by the nuclear density. And here we have to be careful because my nomenclature previously had a rho in it, which was the density of neutrons. But now I like rho so much that I'm going to reuse it, having basically dispensed with this part of the calculation. I'll reuse it to talk about the nuclear density in the material. So that is now going to be what the potential is. And here comes an interesting observation, which is that you remember that I was sort of fiddling around with the sign of the scattering amplitude. There's an interesting minus sign, which you'll have the pleasure of deriving in one of the homework problems. And you could say, well, does that really matter? Because he's constantly talking about scattering cross-sections that involve the mod squared scattering amplitude. And here you see very, very clearly that when I operate in this limit where we treat the material as being sort of a smeared nuclear potential, then actually the amplitude matters a lot. The sign of the amplitude matters a lot. If it's a positive sign, then we actually have a repulsive potential, whereas if it's an attractive sign, then we have an attractive potential. Now it turns out that with the sign convention I've used, B is generally positive for most nuclei, but not all nuclei. There are a couple of examples where this actually ends up being negative, and once again, I'm not going to actually be able to say exactly why that is. In fact, even Fermi started off with the opposite sign, and gradually he found that the signs were all coming out negative. Then he switched it, and from then on, we've been working in that fashion. So good. So let's think about this kind of situation. I want to just solve a very, very simple sort of a boundary value problem, if you will, in this approximation, which we can call sort of a neutron optics type spirit. Okay, so I'm going to think about the interface between a solid, which will be below the line, and a vacuum, which is above the line. And let's think about a neutron beam incident onto this interface as such. And it'll start off with an energy, kinetic energy, which is equals to h bar k squared over 2m. And that will be the wave vector within the vacuum for this neutron. And then it has to enter the solid. Now inside the solid, the potential energy has actually increased, we claim, according to this smeared Fermi-Soda potential. However, the energy cannot change as I pass through this interface. It's an elastic process. If you want to think about it from a sort of electromagnetics perspective, then you won't be able to satisfy the boundary conditions if you were to change the energy from this side to that side. The wave function has this time phase factor in it, and it has to be, the boundary condition has to be satisfied at all times. So I really need the energy to be the same across this interface. No exchange of energy is occurring, and therefore I can write that within the solid, the energy is going to be h bar k prime now squared divided by 2m plus this term, 2 pi h bar squared divided by m times scattering length times the nuclear density in that material. And you can see that if B is indeed positive, being a repulsive potential, then I'm actually going to have to invest some potential energy and correspondingly reduce my kinetic energy and therefore increase the wavelength or shorten the wave vector. So k prime in this situation, when B is positive, is actually going to end up being a little bit less than k. And this is quite interesting because that's exactly the opposite of what happens in optics, so with photons. in regular optics with light, you would go from if you go from a vacuum to a denser optical medium, then you're going to find that the wave vector actually becomes longer in the denser medium, and that corresponds to an index of refraction. Index of refraction would be defined as k prime divided by k, and in the case of neutrons, because of this, when b is positive, I'm going to have an index of refraction for the material which is actually less than 1. So this is what we're not allowed to do in optics, because then we would somehow, at least we have to go through a lot of effort to try to produce that type of situation. So for neutrons, that is basically what tends to prevail. So let's try to do the little calculation to think about this situation. So we won't do it very formally, but you can probably imagine that there is going to be a reflection process, and this type of thing, that's a neutron reflection situation. So this would be an incident angle, and this would be a reflected angular reflection. They have to match each other in this type of specular reflection process. But there will also be a transmitted beam. Neutrons will be able to enter this material, and what's going to happen, as we said, the wave vector is shorter, but to satisfy the boundary condition, I need the projection of the wave vector to match. The projection of the wave vector onto this interface plane needs to actually match. This will produce Snell's law, and that means that this angle of refraction, is actually going to become less than the angle of incidence. Now you'll notice that I'm using angles to the interface, and this is to prepare you for later discussions by Sunny Sinha, in which he's going to talk about the experimental utility of this kind of reflection experiment. And it turns out that with neutrons, we just generally want to use those angles rather than what is occurring in optics, where we typically use the angle to the normal. So that means that Snell's law, in our case, Snell's law actually looks like this. It's going to say that k cos theta I, that's the projection of the incident wave vector onto the interface, has to match k prime, the length of the wave vector in the medium, cosine theta refraction here. Okay. And as I said, k prime is actually less than k, and I'm going to define this as my index of refraction. So that means that if I was to divide by k on both sides, I get that cos theta I must be equals to n cos theta refraction. Okay, and now here comes a very, very interesting property. Because if you can imagine sort of reducing this angle of incidence, at some point I'm going to get to the situation where this refracted beam is sort of traveling right along the surface. And at that point I have what's called the evanescent wave in the medium, and there's going to be an attenuation of the neutron density as I walk perpendicular to the interface in this direction. So all of that is just exactly the same as in optics, because it's the same type of boundary conditions I'm dealing with, and it's the same type of plane wave situations that I'm talking about. So we will have the phenomenon of total reflection, but in this case it's total external reflection. So it's when I come from the vacuum to the dense medium with neutrons that I tend to have total reflection. Whereas in the case of optics, it's in the reverse. You always have to come from the dense medium into the vacuum in order to have total internal reflection. So we have the opposite with neutrons, and that turns out to be really, really useful. I'll tell you a few words about that. But first, let's find the angle of the critical angle for total external reflection, and that happens when this cosine becomes 1. That means when the angle of refraction becomes 0. That means that the critical angle is defined by this expression, cos theta critical must be equals to the index of refraction. Good. And so now I think I should just develop a little bit the expressions for this index of refraction. I wrote what the definition of it was, but now I should play a bit with these two equations to actually back out what the index of refraction will be. And then we're also going to just take a numerical example of that. Okay, so I can equate these two expressions to each other, and I can multiply by 2m, rearrange things a little bit, and you'll see that it says k squared equals to k prime squared. And then I have to be a little careful here, and then it says plus, I think it would be a 4 pi h bar b rho, something like that. It seems appropriate. Good. All right. So then let's divide by k on both sides of the equation, and then I'll find that 1 is equals to n squared plus 4 pi h bar b rho. Oh, I thought there was something wrong here. I think there's something not quite right. Let me just check my notes. I try to be a little. So let's see. So okay. So let me. Okay. Let's go through it together to make sure we get it right. So we had, what do we have there? 2 pi h. Oh, this is why I hadn't. Sorry. Should be okay. It just says h bar squared. So all of that should have gone out as we would expect. Yeah, I knew something was not right because we're not really, once we're in this optic limit, we don't have h bar to contend with anymore. So that's what it should look like. And then I'm going to divide by k on both sides, and I'll end up with this expression. So we said k prime over k equals to square root of 1 minus lambda squared b rho divided by pi. Oops, sorry. And now what did I do with all my pi's and so on? Just remember that as I divide by k, I'm also dividing, I'll be dividing by 2 pi over lambda, and somehow I'm trying to bring out lambda in these expressions, and so that's why I end up with a pi sitting downstairs. So you might want to just try those expressions a little bit, and in fact I think there's a factor, seems to be a factor of 2 there. Yes. Okay. So then I'm going to put this into the expression for the angle of total external reflection, and I'll look at the limit of very, very small critical angles, because they will turn out to be very small. So I can use the Taylor expansion for this guy, and it says I'm sorry, there's not a 2 there. So I use the Taylor expansion here, and it gives me a half theta critical squared equals 2, and then I've also Taylor expand this guy here, and it produces 1 minus a half. That's where I need my half. Okay, lambda squared b rho divided by pi. And so now I can just rearrange this expression to directly read off that the critical angle is going to be equals to the square root of b rho divided by pi, and I do have a lambda sitting out in front. So this is the expression I was trying to get to. So it tells you that the critical angle is going to grow with the wavelength. So longer and longer neutrons will produce a larger and larger critical angle. And it's also just a really beautiful expression. You can check that it has the right dimension. B was a length. This was an inverse volume. So this becomes a length squared, square root of that. This becomes an inverse length squared, square root of that is inverse length, cancels that. So it becomes dimensionless as it should be. And so now we could just try to pop in numbers for some appropriate material. And so let's think about nickel 58. For nickel 58, nickel 58, there we have it. B is equals to 4.15 femtometer. Femtometer 10 to the minus 15 meters. And you might say, where does he get those numbers from? So in the homework problem, I have a reference to a website that has a beautiful periodic table where you can read off all these scattering lengths. You can, if you just Google neutron scattering lengths, you'll immediately find things and so on. So that's pretty straightforward. And then we do 10 angstrom neutrons. That's a perfectly reasonable wavelength. And then we can derive the nuclear density for nickel, and it turns out to be 0.5 times 10 to the 23 inverse cubic centimeter, similar numbers as hydrogen in water, etc. So those don't change very much. I put in the numbers, and I get a critical angle of 0.0081 radians, which, when converted to degrees, multiplied by 57, which is 180 over pi, I get this is equal to 0.47 degrees. So that's the critical angle for total external reflection of 10 angstrom neutrons off a very flat surface of nickel-58, that particular isotope. So it turns out that nickel-58 is particularly good because the scattering length is quite long and it doesn't have incoherent scattering. And we'll say something at some point about incoherent scattering. We haven't mentioned it yet, but that will sort of muddy the waters if we were to try to use a material with strong incoherent scattering. So nickel-58 and total external reflection is actually the way that we use, or the technique we use to transport neutrons over large distances from the nuclear reactor all the way out to a guide hall or some location where we can do the experiment. Neutrons are simply traveling through this total external reflection process in a neutron guide, which is basically a very, very long tube, evacuated. It could be made from glass, coated on the inside by, could be nickel-58, or it could be an even more ingenious combination of thin film structures to enhance the critical angle for total external reflection and to allow a large angular divergence to be transported through this guide. So this is a pretty advanced technique, and it's one of the reasons that neutrons actually can be as successful as they are, because we have these essentially like neutron guide networks that we can create using this technique. Okay, I think that I should have asked if there are any questions so far from anyone. No questions? Okay, if anyone has a question, they can just type it into the frame there. Okay, so okay, now I want to. I've got various things we could talk about, and I think I'd like to say one thing more about this total external reflection process, and I want to tell you a very, very elegant experiment that is used to actually measure these scattering lengths. You might say, well, if you can't calculate them, how are you going to actually measure those things? And of course, we have now shown that the scattering length is directly related to the critical angle for total external reflection. So there's an experiment you could do. See when do you reach that critical angle. And that is a way of doing it. But there's an even more elegant way of proceeding, which is just really beautiful. And so the idea is the following. And this now gets... Okay, so let me show you what it is. So you create a surface of the material whose scattering length you'd like to measure. And then you arrange for a situation in which the neutron beam, the height between the location where the neutron will emerge and the surface of the material whose scattering length you'd like to measure can be varied. Now, typically, the height of the neutron beam will be somehow fixed because it comes from a reactor, comes from a guide network or something. So you could lower the surface appropriately, come up and down. And of course, the neutrons do have mass, so they have projectile motion, and so they're going to just be traveling out like that, and then they will imagine that I have some way of bringing them to this point, having them come out of this aperture. From that point on, they're just executing a normal projectile motion. Of course, this projectile motion will depend on what the velocity of the neutron is, but you'll see that that actually cancels out in a really beautiful way. So what happens is that if you were to increase this height sufficiently, then what happens is that there's not enough downward velocity to actually enter into this material. So you could think of it, let me think of it an even more extreme situation as follows. If I was to consider this to be a neutron, and then I would make the angle for total external reflection actually be equal to 90 degrees. And that's possible if I make the wavelength long enough, and people do that. Then it needs to be really into the ultra-cold neutron range. Then you can actually have the neutron come down, hit the surface, and just bounce up again. It cannot enter the surface because of the repulsive Fermi soda potential. So you can actually contain neutrons in a bottle using this type of technique. So it's essentially that type of experiment that we are mentioning here, which is that if this surface is high enough, then I will simply have a kind of a bouncing process. On the other hand, if I lower the surface sufficiently, then the neutrons will have acquired sufficiently downward velocity as they reach the surface to actually enter the material. So that means that there's actually a critical height for total reflection of the surface, which does not depend on the velocity of the neutrons as they emerge at this point. And in fact, the equations are absolutely trivial, which is that the energy, the potential energy, the gravitational potential energy of the neutron, mgh critical, at the critical height will exactly match the Fermi-Soda potential associated with the neutrons entering the material, which we have written over there. So that's 2 pi, what was it, h bar squared over m times scattering length times the density. So if I can go and measure this critical, if I can go and measure this critical height, then I'll be able to rearrange this expression. I have to be careful. This is not the Planck constant. So this is just the physical critical height. Then I can go and measure the scattering length. So in other words, just rearrange this, and you'll have a beautiful technique for actually measuring the so this becomes squared, right, and then comes divided by a rho and divided by a 2 pi h bar squared. So this type of expression would allow you to measure the scattering length. And that's one of the ways that people use to measure these scattering lengths. It's also an example of a very clever experiment in which I don't have to monochromate the neutron beam. I don't have to make sure that they all have the same energy. It doesn't matter what energy they have, it's still this expression. So I can use a broad band of radiation, and that allows me to use more of the neutrons. And remember what I said, that the flux is always something we're really fighting with. So that's an elegant little experiment. Okay. All right, so that was basically a little bit about neutron optics. And then I have about 25 minutes left, and I think, let's see, I think I will go straight. I'm going to put a little bit aside here. I'm going to put a little bit aside here a couple of pages that talk about absorption of neutrons. And so this I haven't spoken much about. And if we find time in this lecture, I will mention something. Some nuclei do have a big appetite for neutrons, if we may say it like that. For example, boron-10 would just love to become boron-11, which is a predominant isotope. And so it has a large absorption cross-section. Cadmium is another example. Gadolinium is another example. So these are materials that are hard for us to do neutron scattering experiments on unless we isotopically purify them. On the other hand, we can use those materials to absorb neutrons. So we can use them when we want to absorb the beam. If we want to shape the beam of neutrons, then we would use perhaps boron, perhaps cadmium. And we could say a few words about this process. The really strong absorbers like gadolinium and cadmium typically have actual neutron resonances that one is working off. And a consideration I just want to mention, I don't want to fail in mentioning it, is that when we absorb neutrons, we will typically also be activating the materials, or we will be generating secondary radiations. And so, for example, with cadmium, which I did mention, illuminated with neutrons, you get a very hard gamma radiation coming off from the cadmium. So you do absorb the neutron beam, but you create instead a radiation hazard from this hard gamma radiation. So these are just, there are quite some considerations that come in as we begin to consider the use of absorbing elements in our experiment. But I'd like to now jump towards something which is very pertinent for the next set of lectures, where Takeshi Igami is going to talk about using neutrons to probe structure. I want to talk about the expressions for the diffraction cross-section when we have a periodic arrangement in our material, so some sort of crystalline material with a periodic structure. And in this course, we're going to pretty much, I think to a significant degree, focus on materials that are in some crystalline form. It doesn't mean that neutrons cannot be used to probe materials that are amorphous or liquid-like. I mean, that is indeed, those materials are perfectly fine to study with neutrons as well. But we're going to develop the formalism which pertains to really periodic structures principally. So let me write a few formulas regarding that. So now we go, in a sense, from the limit that I just talked about, which was the limit of geometric optics, where I do not worry about interatomic interference. That was explicitly what I was trying to abstract from in the previous discussion. Now I'm going to go in and talk specifically about interatomic interference processes. So this type of neutron optical description that I described does not apply to describe those phenomena. It doesn't mean that there are not neutron optic phenomena associated with periodic solids. It's just that I have to go into the correct limit to appreciate those. And now I'm going to go into the other limit where I do have the interference effect. So where the wavelength of the neutron does match the spacing of atoms in the material. So again, it's going to be diffraction from a rigid periodic structure. And I'm going to write my potential in a very general and simple form, actually. So again, it's an interaction potential between the neutron and the sample, and it's going to be written as a sum over all the many unit cells in the material of a potential which I won't decorate with a twiddle. So the twiddled one is the potential for the entire crystal, and the untwiddled one is the potential for the unit cell of this material. So I didn't tell you exactly what the unit cell looks like yet. I'm going to leave that to be a mystery, and we can eventually figure that out. But all I want to focus on now is the fact that the overall potential appears as a sum of identical terms, displaced by this vector which I've written R subscript L. Now, what is R subscript L? I'll get back to it in somewhat greater detail later, but I will be thinking about a Brevet lattice, and the subscript is simply visiting each of the unit cells in the Brevet lattice. But to be more specific, subsumed in this subscript are three indexes, which would be m times some Brevet vector A plus n times a Brevet vector B plus, let's say, j, mnj, times a Brevet vector C. So this L is basically the set of these three indexes that I'm going out to visit. Okay. So now let's see, what does this scattering amplitude look like? Because as we said, if I know the scattering amplitude, I know the differential scattering cross-section is just the mod squared of the scattering amplitude. So my first step is to calculate the scattering amplitude. So that would be f, we call it f theta, and theta is a kind of a little mysterious. You can say, why does he have this theta in there? It's basically just to remind me that this one does have angular dependence. But now we're really going into a situation where we have very extreme angular dependence, because we're going to have all these interesting interference effects from the crystal. But still, I'm just keeping the theta there for now. Okay, so the expression that I'm supposed to calculate is like this: m divided by 2 pi h bar squared. And then I'm supposed to do a Fourier transform, so d3r, of my full potential. So it's e to the I q dotted with r. And remember that q is wave vector transfer, k incident minus k scattered. And then I'm going to have here my summation of L, v to the r minus rl. So that's what it looks like. Okay, so what I'm going to do now is I'm going to make a substitution in this integration. I'm going to introduce a variable u, which is equals to r minus rl. So r is my variable of integration. rl is visiting each of those many unit cells. Introduce that variable, which means that r itself is going to be equals to u plus rl. And then just continue writing this expression. And let's see, I'm going to take it just slowly because I think this is sort of important just for you to notice how this works out. So there's an e to the I, and then there's a q dotted with r was u plus rl. So u plus rl. And here I have to be careful because I need my summation over L. I'm going to have to switch those. So that's that one. And then comes my V, which is now just a function of that U vector. And the integration, I still wrote it over R, but since those are just shifted with respect to each other and it's complete integral over space, I can just change that to a U variable. And then comes following step. What happens is that you can see that this RL no longer shows up inside the position-dependent potential, and so I can actually write summation of L, and then comes my e to the I q dot RL. Okay, so that's everything that depends on L, and then factored out is an integral d3u, so it's a sort of a position space integral of e to the I q dot u v of u. Good. So that's my that's what's happened essentially as a result of periodicity, because I have this periodic. Actually, I take that back. This is not. I don't need periodicity in a sense at this point. All I need is that I have copies of the same object in many, many locations, and then I'll get this kind of factorization occurring. And I want to just, if you could move a little bit over here, I'm going to introduce the following nomenclature to simplify the expression. I'm going to denote b of q as being equal to this integral, so the d3u e to the I q dot u v of u. So this is a Fourier transform of the interaction potential within one of my copies that exist in this material. Introduce that, and then I can actually write a very, very nice expression. I will just write the full partial, or the full differential scattering cross section now, because that would end up being equals to the sorry, let me do one little trick. I'm going to let this term here, let me have that absorbed into this expression here. So I'll just have this minus, what was it, m divided by 2 pi h bar squared. And the reason I like to do that is that now this has dimension of a, it has dimension of a length. So now it has, yeah, that's correct. It has now a dimension of a length. Good. And so here I have, I'm going to have a mod squared of bq, because remember the scattering cross-section had to do the absolute squared scattering amplitude. And then I have my sum over L e to the I q dot RL. So the consequence of having this repetition of many units in my material is going to be a overall prefactor, which we could call, and which in many cases will be an atomic form factor. So it basically has to do with it has to do with the Fourier transform of what I have within my unit cell, and then I have this famous lattice sum, which of course I should take the mod square of. Okay, so this guy, and if I have a periodic structure, because of it being periodic in real space, it will be periodic in reciprocal space, and it's going to be a very spiky type of function. And we're going to, let's say a few words about the behavior of this term here. And so this I'll do all the way over here. Maybe the camera has to come along with me. So let me say a few words about this term here. So I have to take mod squared, which means that it actually becomes a double summation. I'm just going to write it L prime e to the I q RL minus RL prime, right? Because one is complex conjugated. I've got a sum over both of those. And now I'm going to use periodicity. The thing is definitely periodic at this point. And what I can say is that each of these sums for a given value of L prime, I'll get the very same sum showing up again. So that means I'm going to get n copies of this sum, n being the number of unit cells in the material. So this is just going to be equal to n times summation of L e to the I Q R L. This type of thing. Okay, so then you could say, can this ever be different from 0? Because I'm summing over a terribly large amount of different values of RL, so all these positions on my lattice. And in the general case of Q, those phase vectors will just produce a horrible mess and eventually average out to 0 at the very, very end of the day. However, it does not happen if this dot product of Q dotted with RL, if that happens to be equals to 2 pi times an integer, some integer, then all of these just become 1s, and now you're just constantly getting the same thing, which will eventually add up to something terribly large. So you have a function which is generally 0, but then it has these very special places where it actually ends up producing something very large. So let's think a little bit about what is the nature of those very special places. What type of values of Q would ensure that the dot product of it with all of the locations of the Bravais lattice actually ends up being just 2 pi times an integer. And the little construction that I'm sure you're familiar with, and yet I just want to make sure that we're sort of on the same page because we come from various walks of life. The construction is the reciprocal lattice that we need here. And basically I'm going to define a lattice which is what we call the reciprocal of the original Bravais lattice, which I wrote down over there, and we should probably have the camera point to this location to remind you of this expression for the locations of each of those unit cells. I'm going to consider the so-called reciprocal lattice, which is constructed from Bravais reciprocal lattice vectors, which have the following characteristic. And I'm really going to exercise the camera walking all the way over here, and John Shackleton. And then we're going to define the lattice, reciprocal lattice, in such a way that A star dot A is equals to 2 pi, B star dot B is equals to 2 pi, and of course C star dot C is equal to 2 pi. So this will define a so-called reciprocal lattice. Whenever I give you A, B, C, you should be able to derive an A star, B star, and C star. And we won't spend a lot of time saying exactly how you obtain those vectors. The most important thing is that it's possible to obtain those vectors. So as a reciprocal to the cubic lattice, we find once again a cubic lattice. Reciprocal to the hexagonal lattice, we find once again a hexagonal lattice. Reciprocal to FCC, we find BCC, etc. So there's a direct connection between the real space lattice and the reciprocal space lattice. And what happens there is that if I was to take a wave vector which is composed of H A star plus K B star plus L C star, then with these definitions I will ensure that tau dotted with RL, RL being one of those special places in the Bravais lattice, this is simply equals to, I'm going to write it out, so I have H A star plus K B star plus L C star dotted with M A plus N B plus J C. So that was the real space and the reciprocal space. When I dot those with each other, then I will ensure that I get 2 pi HM plus KN plus LJ. So 2 pi times an integer. Now, I forgot to mention one thing. I should have mentioned that. This is not the sufficient condition. I also have to ensure, apart from these dot products being equal to 2 pi, I want to ensure that all of these sort of off-diagonal terms, if you will, A star dotted with B, should be equals to A star dotted with C, should be equals to 0. So I need to be perpendicular to 2 of the real space directions, and I need to have a finite component along the other direction, and I'll arrange for the length of the reciprocal lattice vector so that the corresponding dot product becomes 2 pi. So that's the reciprocal lattice. I'm sure most of you have seen it, but some of you may not exercise it as much as you do when you're doing scattering. So when we're working with either X-rays or neutrons, then this is basically the space that we live in, the reciprocal space. Okay, so what happens then for those particular values of Q, as we've shown here, the dot product ends up being equals to 2 pi, and then all of these terms will add on top of each other, and I get a finite value. So now I'm going to double back to this location. Okay, so what's going to happen then is that my wonderful expression for the scattering cross section, d sigma d omega, I'm going to repeat it here. It has my unit cell Fourier transform, if you will, and then multiplied by a set of delta functions, direct delta functions, because only when Q matches these reciprocal lattice vectors will I have a finite value, and whenever I'm not at those places, then I have 0. So that's what a direct delta function looks like, Q minus tau, and it's a summation of all of those reciprocal lattice vectors which are spanned by A star, B star, and C star. And of course I need to make sure that the dimensions of this are correct. You remember that we had an n already had shown up because of the way I dealt with the double summation in the step going from here to there. So going from here to there, I picked up an n. I had to remember that n, and that showed up here. And so then I have this summation of delta functions. Now the dimensions are not correct yet, because this has dimensions of a length to the third power, and you have to work out what that prefactor is, and that turns out to be equals to 2 pi to the third power divided by the real space unit cell volume. So that is now the expression for diffraction. We've derived it from the very bottom. The expression for diffraction from a periodic structure which has this Fourier transform of the interaction with its with what's in a unit cell, and which has these points in the reciprocal lattice. Now, let me draw a little sketch of this. I'll remind you that Q is equals to wave vector transfer k minus k prime, incident wave vector minus scattered wave vector. And I could draw a little picture like this, that this would be the incident wave vector, and this would be the scattered wave vector. Draw them tip to tip so I can easily calculate the subtraction here. So this would be k prime. The vector that goes in this direction would be wave vector transfer, q. And what we've seen in this expression is that I'm only going to get diffraction when this wave vector transfer matches a reciprocal lattice vector in length and in direction. Now, if we think about the length of this vector, if we denote this angle as being 2 theta, then then the length of Q, let me write it here, length of Q is going to be equals to k sine theta gives me this, and there's another k sine theta, so that's 2k sine theta. That's the length of, sorry, that's butting up against this, not so good. Okay, so that is the expression for the length of wave vector transfer, and this is essentially what we would call, some people will call it, or we would call it happily, Bragg's law. Now this is written in reciprocal space, and sometimes you'll see people write it n lambda is equals to 2d sine theta, and this is exactly the same, just written out in real space instead of in reciprocal space. Okay, so I think there you basically have the story, and I don't know if are there any questions at this point from anyone? No one is typing questions. I think maybe the main thing I think you're now ready to to enjoy Takeshi's lecture next week. And maybe the only thing I just want to, in the last minute or so that remains, I just want to point out that there are some things missing in this. Even though I basically brought it up from scratch, we were dealing with a completely rigid potential. So there's no motion at all, and of course this is not acceptable because there will certainly be zero-point motion of the atoms, and if we go to a finite temperature, there will be thermal motion of the atoms as well, and all of this will have an effect. And the sort of the zeroth order effects that you'll see show up is that the interaction potential, which we had postulated as being a delta function, right? We had this Fermi-Soda potential, so that if I was to be in a situation of a Brevet lattice where there's just one nucleus per unit cell, then that nucleus has a delta function interaction potential, and the Fourier transform of that, in the case of just one nucleus per unit cell, then B of Q just becomes equals to the scattering length in that case. And so in that case, this is just a constant essentially. But then what happens if I have zero-point motion or thermal motion is that this delta function is actually somewhat spread out because the atom has a finite extent beyond the size of the nucleus. And that will cause this Fourier transform to be Fourier transform of something that's a little bit larger in real space, which means that it'll actually become smaller in reciprocal space. So our formulas that we had here would produce exactly the same intensity for all of the delta functions going all the way out to extremely large values for momentum transfer. But what I'm telling you is that as a result of zero-point motion and thermal motion, we would expect that the higher Q peaks will actually be attenuated because the potential is somewhat spread out in real space. So that's something that I'm sure Takeshi will come into to describe to you. And then just to give you a preview, what goes on then beyond that is to extend from this description of essentially a rigid material also to include the possibility of having excitations created in the scattering process itself that is exchanging energy between the neutron and the material. And that's something I will discuss when I come back after Takeshi's lecture. So with that, thank you very much, and I hope you'll be able to decipher some of the notes that will be posted and make some progress with the homework. If you have grave issues with the homework, you can probably send me an I don't know if I should do this, but I'm happy for you to send me an email with your questions. I don't think they're too hard, but I can help you along if there's a problem. Okay, thank you very much. Good evening.